first name is Shin-ichi. So maybe, can you say this? Shin-ichi. Oh, okay, good. So I think it might be a little bit difficult to pronounce my first name, Shin-ichi. So Sasa is much easier to pronounce it. So say you can call Shin-ichi or Sasa. Sasa is okay, right? And also in Japan, sometimes, many people say Sasa-san, right? This is a standard calling. I mean, of course, you can choose Shin-ichi, okay, and as him and Sasa, okay, of course, and Sasa-san is better. And this is my name. Maybe you know that I present my lectures in English. So my English is, of course, typical Japanese English. So maybe you sometimes miss my words. So in that case, you ask without any hesitations and what is wording and what are you saying and so on, right? And also, I sometimes cannot hear your quick English. Your English is too fast, right? So I'm very welcome to have questions, but please speak slowly. This is very important point, right? So communications are very important, And if you speak slowly, maybe I can find it. And if I speak slowly, and maybe you can find what I say. So this is a general remark. And yes, so I just start with my final purpose. This is not final purpose of this lecture. This is the final purpose of my life. So something my dream, right? When I was undergraduate student, I studied quantum mechanics. You studied? Oh, maybe yes. And also general relativity, you see? A little bit, yes. Many people a little bit, yes. And I clearly remember that these subjects are really exciting. And I learned textbooks through the night with much excitement. Okay, but sometimes I found that after studying the textbooks, maybe in quantum field theory, birds are singing, right? Yes, birds are singing, and wind is blowing in Japan. No, not is blowing, but wind is blowing, right? And birds are singing, and we are communicating with you by conversations. This is very, very familiar to us. Nothing surprising, because we all experience such phenomena when we were babies. But these are really surprising if we start to consider natural phenomena on the basis of microscopic fundamental physical law. This is just synchronization of about things, right? And I determined my research subject at that time. I would like to understand these natural phenomena from the microscopic fundamental physical rule. This is the quantum mechanics, quantum field theories, and Hamiltonian systems of atomics and molecular and so on. So more precise things, I say that I'd like to understand emergence of orders. This is the final dream. But of course, this is quite difficult. And now it took 30 years since I decided to choose my subject, but progress is very, very tiny. And we don't understand at all, but we have very small self-understanding. And one important step in this direction is non-equilibrium statistical mechanics, which aims at understanding non-equilibrium dynamical behaviors on the basis of microscopic mechanics. This is a non-equilibrium statistical mechanics. And of course, this subject has been studied over the 20th centuries. I don't explain, say, maybe you know, you can know the linear response theory. This is a very famous framework, and also projection operator method, projection operator method. These are typical achievements in the progress of non-equilibrium statistics mechanics in 20th centuries. And after that, this was about the 1950s, and this is the 1960s. After that, activities, research activity in non-equilibrium statistical mechanics decreased. Why? Subject become more and more difficult. Of course, famous Kawasaki developed the nonlinear projection operator method and proposed a nonlinear response theory. But maybe you don't know the name of nonlinear response theory at all, I guess. And also, some non-equilibrium ensembles was proposed. But these are too formal and too complicated and too difficult. So everybody escaped to study the non-equilibrium statistical mechanics, and you can look at the chaos. Chaos might be more interesting, and the oscillations and pattern formation and so on. So everybody just jumping into the different research subject. This is a history of non-equilibrium statistical mechanics. But the situation has been changed. Eraser. Oh, yes. Oh! Difficult. Situation has been changed. Now, 21st century. 21st century. No, 21st century. 21st century. Situation has been changed because of the discovery of fluctuations. Fluctuation. Oh, maybe you find that my character also dirty, and maybe you can guess. If you cannot read it, please tell me that it's better to fluctuation cell. This was discovered in 1993. This is just nothing but symmetry properties. Symmetry properties of large deviation function. So maybe you are not so familiar with large deviation functions, and symmetry properties are symmetry properties. Looking at this expression, you might think that this is just so of course this is a discovery, but this is just a discovery was one property of one quantities. Yes, and at least at that time, everybody didn't take so seriously these discoveries. Of course, the symmetry properties might be always interesting. And so someone asked, what is the condition of the symmetry? What is the class of systems that exhibit such type of symmetries? And but apparently, this properties is not related to the essential aspect of non-equilibrium system mechanics. But now, 2015, everybody knows, specialists knows fluctuation theorems. This is actual. This is say common common knowledge about the specialists. The more important thing is that we can understand many complicated statements by using this symmetry properties. We don't understand deep reasons for this, but this is the fact that when, okay, suppose that we want to understand some macroscopic behaviors on the basis of microscopic dynamics, then as I said before, it was quite difficult to understand macroscopic behavior beyond the linear response regime. But if we use these properties, we can find shortcut to propositions, claims, results. That's why this discovery is now regarded as an important achievement. So now I explain my outline my talk. Yes. Here's. I first explain large deviations. One day. Today, I explain what is my large deviation. Maybe I assume that you are not familiar with large deviation functions, and I give you informal discussion about large deviation functions, large deviation theory, with particular emphasis on physical aspect, not mathematical aspect. We just focus on the physical aspect is more important. And this is a highlight. This is today, and the highlight is Einstein formula. Of course, there are many Einstein formula. So today's Einstein formula was discussed in 1908. Maybe you don't know, right? How many Einstein formula do you know? 4 or 5. 4 or 5? Oh, or maybe you know that. Oh, you are so smart. Oh, okay. Maybe this is the first, and okay, no. Okay, this is a highlight on today, and tomorrow I discuss what I will discuss. Yes, applications to dynamics. Application of large deviation. Application of large deviation theory to dynamics. And this is basically Onsaga. There are many Onsagas, but how many Onsagas were? Oh, just one. When? 1943 or 45? 1943. What paper? Which paper? Oh, okay. Yes. This discusses exact solutions of two-dimensional Ising model. Yes. This is, of course, this is very famous papers, and I will explain the Onsaga's work in 1931. He got Nobel Prize by this achievement. But usually, Onsaga, of course, we can read Onsaga's papers, but it is quite difficult to understand what he wants to discuss. Actually, when I was a graduate student, I tried to understand Onsaga's paper, but my attempt turned out fail. it is very abstract and very, how to say, genius. But now, of course, I am now successful to interpret this work. And in my lecture, I explained the basic idea of Onsager on the basis of Rice deviation theory. On the basis of microscopic mechanics. This is, of course, the result is actually the same, but our viewpoint is completely different, right? And tomorrow, yes, here is Tuesday, and Wednesday. What this? Yes, I will discuss second law of thermodynamics. Of course, maybe you know that second law of thermodynamics, but I think that you are not so familiar with microscopic understanding of the second law of thermodynamics. Of course, this subject is quite difficult. You know, so there are many points of discussions in the argument of the microscopic understanding of the second law of thermodynamics. So I will carefully separate the points of argument, and we discuss the second law of thermodynamics on the basis of microscopic descriptions. And in that case, we this is actually this is not highlight. We have another highlight, but I will introduce Jaruzelski papers. Jaruzelski papers, 1999. Precisely speaking, Jaruzelski equality was discovered independently from fluctuation theorems, but now we are now understanding. We now understand, and Jaruzelski equality is a kind of variant of fluctuation theorems. So this is just introduction. This is introduction. But I actually, as I said before, there are so many points of discussion, points of argument. So of course, this equality cannot completely solve the microscopic descriptions. But one aspect of the second law of thermodynamics can be clearly described by Jaruzelski tricks. And this is just the introduction to fluctuation theorems. And Thursday, why? Yes, identities. So actually, this is a variance of fluctuation theorem. So original fluctuation theorem is just one, but there are so many fluctuation theorems. So I will explain why such so many identity appears, and I will tell you a few important identities. Important means that useful identities for understanding the connection between macroscopic behavior and microscopic descriptions. Yes, so yes, this is identities, and also you can say this is symmetry properties of large deviations. Yeah, I found that the title of my lecture is a symmetry of large deviations. Is it right? I never write such title. Organizers determine the titles, and you talk about this title. So I respect this proposal, and this is a highlight of my lectures. Okay, and Friday. I actually, honestly speaking, still I don't determine it yet. I have several choices, and maybe Friday and Saturdays. I would show you. This is how to say this is main achievement of my lectures, but you don't understand how do you use these identities. So I want to show you the way to use these identities. I mean the applications. Applications of the identity, application of fluctuation theorems. Derivation of fluctuation theorems are very, very simple. Not so tough and not so deep itself. But as I said, application of fluctuation theorem is quite powerful. One example is derivation of hydrodynamic equations. Derivation of the hydrodynamic equations and microscopic derivations, yes. Suppose that you can imagine turbulence. Turbulence is air is, you can imagine storm, right? So air is violent flows or violently. So this phenomena can be described by hydrodynamic equation. Do you know the hydrodynamic equation? Oh, you don't know that. Oh. Okay, okay, no problem. I will explain. Do you know the hydrodynamic? Oh. Do you know the hydrodynamic? In India, hydrodynamic equation, students do not need to run the hydrodynamic equation.
Some of them should
know. Oh, okay. Oh, I would say that, okay, thermodynamics is very, very beautiful, universal, elegant formulations, and also hydrodynamics is also very simple, beautiful, universal framework. Okay, I determined. Now I determined. Friday, I give you hydrodynamics. Raise a hand. If you know the, if you can write hydrodynamic equation, raise a hand. Or you can write hydrodynamic equations. Okay, but sorry for him, but almost all of you cannot write hydrodynamic equations. So I determined on Friday I'll give you a lecture of hydrodynamics. Or maybe okay, that's okay. This is not a lecture of hydrodynamics, but I think it is very, very important to run the hydrodynamic equations. Then on Saturday, I give you microscopic description. Okay, so storm can be described well, hydrodynamic equations completely. This is actually students learn the hydrodynamic equations, and they surprised that, oh, this complicated behavior can be described by hydrodynamic equation. Wonderful, okay? And Saturday, I gave you microscopic description. Means that air consists of molecule, right? Do you believe that? Maybe. Then storm can also describe by Hamiltonian equations of molecules. Do you believe that? No, yes. But it is, I guess everybody believes that, right? And storm can be described as Hamiltonian equations of a molecule, or quantum mechanics of a molecule, right? Maybe quantum chromodynamics of quark and gluon. Maybe correct. But the problem is, how do you understand that? This is really fact. Storm can be described by Hamiltonian equations of the molecule, but how do you understand this fact? I will explain. Basic idea, how can we connect macroscopic behaviors with microscopic Hamiltonian descriptions? And I give you technique to have a connection between the two by using identity of fluctuation theorem. Actually, this was my recent paper, 2000. Today, 2015. Or 3. I don't remember precisely. But this is a letter. So I'm now preparing a longer versions of papers, and it's quite difficult to read the papers. And it's just the whole pages. So everything is compressed in the whole pages. So it's very, very difficult to read it. But if you are interested in it, all information can be written in the paper. So you can check. You can read these letters, and they can check everything. And also, maybe I will write longer versions. Every calculation can be explained in one paper. But anyway, so this is Saturday. This is planned as Saturday. So here is a plan of my lectures. I changed my lecture. Okay. And are there any questions about? So about manner of lectures or content of the lectures or outline of the lectures, and what else? No questions? For the moment, you can hear my English a little bit. Of course, grammar is completely broken, right? And pronunciation might be a bit maybe difficult, but maybe you can find my feeling, right? Yes. Okay, this is important. No questions? Okay. So, just time over. Now I explained the Einstein formula, so just by using 1 hour. What? Thermodynamics. Let's start with thermodynamics. So, what is thermodynamics?
Dynamics of lot of particles, lot of microscopic particles.
Macroscopic?
Particles, macroscopic particles.
Yeah?
Dynamics of them. Dynamics of them.
What is thermodynamics, right?
Yeah, that is
Thermodynamics is?
a dynamics of macroscopic particles.
Oh, this is full dynamics. Dynamics of macroscopic system is fluid dynamics, right? Thermodynamics does not cover this dynamic of behaviors. What is thermodynamics? In one phrase.
Yeah. So dynamics of
Dynamics of? Oh, dynamics of heat. Okay. I usually explain what is thermodynamics. This is my favorite pictures. This is thermology. This is thermology. And this is mechanics. Dynamics is a little bit confusing. Yeah, almost same in the dynamics, but as he said, the dynamics means more dynamic motions. And so what is thermology? Thermology is the framework of temperature, heat, and mechanics is pressure and work and so on, right? So there are two different areas, research, academic research field, thermology and mechanics. But the important thing here is that there is intersection between thermology and mechanics. So that's why thermodynamics can be said that this is one phrase. Thermodynamics is a unified framework of thermology and mechanics. Maybe you know that electric magnetic theory. Is it right? Is it correct English? And it is a unified theory of electric theory and magnetic theories. This is obvious. You learn that electromagnetic theories. But important thing with electromagnetic theory is that there should be intersection between the electric theory and magnetic theory. For example, if you consider the current, then we can generate a magnetic field. So in the same way, thermodynamics is a unified framework of thermology and mechanics. So important thing is existence of intersections. What is intersections? I just give you one example. Yes. For example, you can say heat capacity. Volume dependence of heat capacity is determined by equation of state. Of course, you can derive these relations if you run thermodynamics. You run thermodynamics? Do you run? Can you derive this relation? Probably, okay. So report, right? I mean the homework. Deadline tomorrow. Okay? No time? Tomorrow. Of course, this is optional. If you want to remember thermodynamics, okay. Of course, this is just exercise. If you learn thermodynamics, but this is more important than exercise because left-hand side is in thermology. Okay, this is about properties of heat. Heat capacity defined is the heat measurement. So, and left-hand side in the thermology, and the right-hand side, this is a quantity. This is properties about pressure, mechanical quantities. So it is really surprising properties. Some property of thermology is related to the property of mechanical properties. And of course, this is one of famous exercises of thermodynamics. And how do we get this type of equations, and how do we have unified framework? Of course, existence of entropy. I don't explain entropy what is. By using, I just say one sentence. For a given material, we specify the functional form of the entropy. This is enough to characterize all thermodynamic properties. You know, heat capacities and the equation of motions and the electromagnetic properties and so on. There are many material properties, But all material properties can be represented by a single functions. If you want to discuss a different type of material property, you just put an argument of the entity function. This is a result of thermodynamics. That's why we can have unified framework of thermodynamics. Okay, so I don't have. I will not have the lecture of thermodynamics. So I just say just examples. Let us consider the following examples. So we first prepared. This is an example of the thermodynamic process. We first prepared two boxes and separated. This yellow line is adiabatic wave, and N1 and N2. This is just setting up. And the system consists of short-range interacting molecules, and thermodynamics is normal, and we can apply the some framework of some standard thermodynamics. Then we just remove wall, adiabatic wall. Then energy exchange occurs, exchange of energy between the two boxes. Then and the final destination was final destination is denoted by E1 yellow. Wait. Yellow. Yes. This is the final destinations. E1 star and E2 star. Okay, you can observe the, this process. Just remove the adiabatic wave, then the energy exchange between the two boxes, and the energy distributions are determined by some rule, and you observe the final destinations of energy distribution. Of course, energy is conserved, so we can have the E1 star equal constant. This is constant. Because the system is isolated from the environment. Then we ask, what is the value? The question is, what is the value of E1 star, E2 star? So what is the value? How do you determine? Do you understand my problem? What is the final destinations? What is the final destinations of E1 star and its energy distributions?
You mean the final energy?
Yeah. Of course, there are many answers, but final state energy redistributed, right?
This will be the average of the
Sorry.
average of E1 and E2.
Oh, but depending on the, okay, suppose that systems are different and N1 and N2 are different. In that case, of course, if N1 equal N2 and V1 equal V2 and material are the same, and of course, expectation of the energy should be same. But in general cases, two materials are different, and V1 and V2 are different, and N1 are different, right? In that case, what is the final destination?
They will be a bit different around E1. Around E1, E1 star
Yeah.
will fluctuate around E1, right?
Yeah.
And I don't know the exact answer, but I can guess.
Yeah, of course, to fluctuate. But what is the final? E1, what is the E1 star? What is the value of E1 star and E2 star? What it determines?
What determines?
Yes.
Okay.
What determines?
Maximization of entropy.
Oh, yes. So this is the result of thermodynamics. Of course, there are several answers. Someone said that this final distribution can be determined in such a way that temperatures are same. This is one way of the answer, of course, right? But if you run the thermodynamics, we know that this is a result of thermodynamics. I don't write. I use additivity. I can use additivity. I omit all. Precisely speaking, right? This is depend on the N1 and V1 and material and something, but we just skip. This is given by max E1 and E2, E1 plus E2. Under the constraint, yes. This is called vibrational principles of vibrational principles. This is a vibrational principle. Vibrational principle of thermodynamics. How do you derive it? How do you derive it? This is assumptions, or can you derive from other things?
This is like equilibrium probably. That is, you count the states, microchemical.
Okay, you use argument of equilibrium states mechanics, right? Of course, there are many ways of understanding, and if we stick to thermodynamics, this principle can be derived by second law of thermodynamics. Second law. I mean, there is no, we cannot extract work in a cyclic process if the system is in contact with single heat bases. This is the second law of thermodynamics. And if we start with the second law of thermodynamics, then we can derive the vibrational principle of thermodynamics under some moderate assumptions. So anyways, this is a result of thermodynamics. And of course, this is maybe I don't explain, but using starting from this expression, you can find that temperature can be defined from the derivative of entropy with respect to energy. Then you can find that in the final destination, you can check that temperatures of the two boxes are the same. Okay, so here is yes, thermodynamics. Now we give next answer, not question. No. Next question. I ask this value. Without thermodynamics. This is the questions. Maybe your answer may be related to the, your answer is maybe gives a partial answer to these questions. And I give you answer to the questions, step by step. You use knowledge of equilibrium static mechanics, but I briefly explain the whole story of the final statement of the answer to the questions. The first thing is that you can imagine the most important point in the first step is energy final destination is given as the most probable value. Of course, you don't. I think that this phrase, you are not so familiar with this phrase. So I give you explanations of the most probable values. So by studying the example. Okay, so I'm now entering a different road, right? I'll be back to the questions after that. But here we just answer. But I mean, this is the most probable value, maybe a little bit terminology to special terminology to the field. So you cannot imagine the precisely what is it. So I think in order to understand the concept of the most probable value, we study the following simple situations. You consider n coins. Typically, of course, 100,000. Of course, it's almost impossible to have 10,000. But you can imagine the 10,000, right, coins. Then you throw 10,000 coins simultaneously. Have you ever done that? No. I guess nobody throw the 100 coins. But my student every year throw the coin because this is the report of my lecture on statistical mechanics. So this is another homework of this lecture. Tonight, you throw the coin over 100 coins. I don't know how many coins are in Indian countries. But you throw the coin, then you check head or tail. Indian coins also have a head or tail? Okay. Oh, okay. I didn't check that. Now I define, right? Plus one. So ice coin head. You just check throw the coin and the head or tail, head, tail. Count. And if the coin is head, you assign the score of plus one. Otherwise, minus one. Ice coin is the tail. Okay? I don't ask the reason. You just follow my guidance, right? Then you just consider the following quantities. Okay. So, what is the value of x? Imagine tonight you throw 1,000 coins. Okay, doing experiment, you just kind of head, tail. Can you predict your result of x? Can be 0.1. Can you predict your result? 0, exactly 0. Of course, it depends on everybody cannot predict the value of x. This is, of course, that's why I ask you throw coins, right? Then, but you can easily, maybe, if you obtained the score, x is 0.5, 0.8, maybe you are upset, right? This is almost impossible. Even if you throw the 1,000 coins, and it is, I can say that you never have the values of the x is greater than 0.8, right? You agree that? Do you agree? Of course, you have some trick. Then if you have some trick, then you have, oh, okay, so you have some Indian magical power, and then you can make a score greater than 0.8. But without such special particular host, we can say that it is almost impossible to have the x is greater than 0.8. So in this sense, very roughly, we can say that x is close to 0. Not exactly 0, but x is close to 0. Maybe you can imagine that this, if you don't imagine that, I recommend you to throw the n coin tonight. Then this is just a game, but we can analyze these behaviors precisely. Suppose that you don't have a special host. Mathematically, this means that probability of head is just equal to 1/2. This is equivalent to the you don't have any host. Then with the assumption that the probability of the head is just equal to 1/2, then we can, this is just mathematical exercise, to have probability of x, probability density. I don't explain what is the probability densities, but maybe you know probability density of x. Density. Roughly speaking, we divided range of x and making a beans and just count the histogram and normalize to unity. This is the probability density. Then you can calculate probability densities. The probability densities is 0 and 1. For example, when n equal 100, maybe you can find something like that. Say, no, I made a mistake. 1/2. Yes. So here is maybe I just calculated very quickly in 100. Yes. N equal 1/2, n 100, and increasing n. So you find that n equal to n equal 1,000, and n equal, yes, okay, n equal 10,000. Indeed, you can calculate and probability density for finite n. So looking at this figure, you can understand it is almost impossible to have the score is greater than 0.8. And value may be close to 0. And now looking at this picture, I define several important consequences. I don't give the mathematical, precise mathematical definitions, but I just give you just imaginations. When n goes to infinity, you can imagine peak becomes sharper and sharper. So n goes to infinity, you can say that x should be 0, right? So this is a law of non-number. When n goes to infinity, x is almost equal to 0. Very, very roughly. The precise statement can be seen in the textbook on the probability theory. So this, of course, if you like mathematics, there are two ways of the statement, weak sense and strong sense and so on, and the difference might be important, but I omit all the discussion. Just looking at this picture, we just understand x is equal to 0 as n goes to infinities. So this is called the law of line numbers. And this value is the most probable value. Okay? This is the concept of the probability theories. Oh, no. I keep this one. Okay. I keep this one. So, this is the most probable value. But this picture say another things. N goes to infinity, including n, you can find sharper and sharper and sharper. So we want to characterize these behaviors. So how do you characterize? of course, you can calculate Px explicitly, so we write the Pnx. Then you can find probability Pnx and 1 over n limit n goes to infinity gives functions independent of n. Actually, in this example, you can calculate explicitly this formula. So this means that this behavior of the probability density is probability minus minus nix. Leading order of the probability density with respect to n is given by exponential functions. I repeat, Ix is independent of n. So it means that suppose that you focus on just x is 0.2, then the increasing n of 100, 100,000, 10,000, then the probability decreases as a function of as an exponential function of n. This is the result, and this is universal. I mean, this is an example of the coin tossing, but you can find many examples of this property. That's why this was named large deviation properties. This property is called large deviation property. Of course, it is a problem that the system exhibits large deviation property or not for a given problem, but if we can imagine, okay, the system might be almost same as the coin tossing cases, then we can apply the, we can assume that large deviation property should hold. So, but anyway, so this is this type of asymptotic behavior is called large deviation properties. I wrote very roughly, and so leading order of the probability density is given by exponential function in a very simple word. And this quantity is Ix. This is a large deviation function. Large deviation function. This is a main character of my large deviation function is the main character of my lecture as well. So this is a concept of a probability theory. Mathematically, this concept was originated in 1968 by Bardhan, a very famous mathematician. But this idea went back to the Einstein, which I will explain now. Anyway, but now this terminology might be popular in physical sciences, so you first understand what is large deviation functions. The large deviation function characterize asymptotic behaviors of around the law of large numbers. Okay, so here is examples, and I just give you a remark. Yes. This is just a remark. Maybe you know that central limiting theorem. Central limit theorem. If we consider the probability of Pnx, then it is close to Gaussian distributions. It is close to Gaussian distributions. this is a central limiting theorem. Yes, this corresponds to the large dimension function is given by quadratic functions. Oh, I use a small character and large character in the same meaning. So x equal x. So no problem. And yes. So this means that central limiting theorem is this is just a quadratic functions. So I write figures. Here is p and x. This is something like very sharp. This is probably distribution of p and x, but ix, which is independent of n, and we have yes, this is curve. And of course, this is bounded on 0 and 1, 0 and 1, 0 and 1. And central limiting theorem is focusing on this regime. Then if we focus on the small fluctuations, then the probability density can be well approximated by the Gaussian distribution. This is a central limiting theorem. Of course, there are some conditions, assumptions behind that. Yeah. Chi. Chi. So this means that central limiting theorem shows that chi is given by no. 2 chi is yes, x minus x star. If central limiting theorem shows that given by chi over n. And in statistical mechanics, we often use x minus x star is chi. And this is called the fluctuation intensity of the in the language of statistical mechanics. If you, for example, if you can imagine the x is magnetization. In the case of magnetizations, fluctuation intensity of magnetization is given by this chi. Chi is the success probabilities. Chi is independent of n. This is a result of central limiting theorem. And okay, here is just one remark. And another remark. I explained the large deviation function just by analyzing just a simple examples. But and in the simple case, I forget that in the coin tossing case, maybe this is another. I don't remember that. Ix is. Oh, I don't write. Oh, yes. In the coin tossing case, we can calculate explicitly the large deviation functions, and here this is the result. Yeah. And in general, this is a coin case. Coin tossing cases, large dimension function can be calculated. But general cases, of course, it is not easy to calculate large dimension functions for given problems. But by using some mathematics, Ix is x star is the most probable value. In the sense of row of large numbers, x star large dimension function is equal to 0 at the most probable value. And also, we can prove that Ix concave functions. convex functions. Convex function. And the definition of a convex function means that if you choose a 2 point of the graph and connect a line, then the always and the graph is below than the straight line connecting the two. This is the definition of a convex functions. So we can prove that if the large division property can be found, large division function is satisfy the convexity properties. Yes, so I don't give the proof. Yes. Okay, so this is a review of large dimension functions. Now, considering this problem again. Considering this problem again. We are studying this type of problems, E1 and E2. Total energy is conserved. And the system consists of a short-range interaction molecules. Then you can divide into the small piece of some systems. This is just imaginations, and the size is much larger than microscopic length scale, but much smaller than macroscopic length scale. Then in that case, this is still thermodynamic systems. Okay? Then you can have some value of energy for each species, right? Then this value is given by summation of each of small systems. Because this is the size is much larger than the microscopic scale, so we can ignore the surface contributions. So we can write something M is the number of the boxes, and y. So this expression is the same as the coin tossing cases. This box take a value, some value, and this box take a value, and we want to know the total. Yes. We want to know the total value. We want the value of the total or energy in the right box. So this is a situation. It's very similar to the coin tossing case. So we can assume, this is just not mathematical proof, we can assume probability E1 and E2. We want to discuss energy distribution of E1 and E2. It's given by we just number of the molecule material amount on material N1 and N2, and we assume the large division properties, and the constraint is yes. This is just assumption. This is not, of course, but the background idea of the assumption is that thermodynamic system consists of many small thermodynamic systems. So E2 is given by summation of the energies of small systems. So we can apply an the idea of the coin tossing cases. Then if we assume the large deviation properties, most probable value. Yeah, yes, sir. Most probable value. And if we take a consider n1 and n2 go to infinity, then E1 and E2 take definite values. These are called the most probable values in the sense of law of large numbers. And the most probable value is determined by 0 of large deviation functions. So if we can calculate large deviation functions for a given system, or suppose that we prepare some systems, then if we can calculate large deviation functions, then the most probable value can be obtained by 0 of the large dimension function. Okay? So the problem now becomes how to calculate. How to calculate. So in order to calculate large dimension functions, we need some assumptions about probability of microscopic realizations. In the case, sorry.
So why you are saying when I equal to 0 is maximum, why not dIgx equal to 0 is the maximum? Because the minimum of I should be maximum of the probability. Minimum of I
Yes.
should be maximum of probability. So minimum condition of dIgx should be
Minimum I means
maximum
maximum
of probability.
probability. Yes.
So the minimum of I is equal to 0 or it has dIgx equal to 0.
Minimum I means the maximum probability. Yes.
Right.
Then
So what is the condition for minimum? It is dIdx equal to 0.
Of course, yes. If I is smooth, minimum value can be obtained by derivative is equal to 0. And of course, many cases, of course, I is convex functions and take y equals 0, some value. Then in this case, of course, the minimum value is given by the derivative is equal to 0. And
It may not be at 0.
huh?
It may not be at I equal to 0.
No, minimum. Okay. I forget to say the general remark. I is a convex and I is positive and I equals 0 at the most probable value. I is a positive. I is positive. I'm sorry, I forgot to explain that. I is positive, but in the case of coin tossing, in the case exactly I is positive and convex, and in general cases, I is always positive and is equal to 0 at the most probable value, and yes, and of course, some cases, this is you can find just strange cases. Most probable values are not always unique. In that case, we can have the and this shape is convex functions of I. So this case, the most probable value not unique. Yes. So in the case of coin tossing, we assume that probability of heads is 1/2. This is assumption of coin tossings. So in order to calculate large division function for these systems, we need another assumptions for microscopic descriptions, which correspond to 1/2 of the coin tossings. Of course, this is not highly non-trivial things, but of course, you know the answers. Principle of equal weight. for the moment, as working hypothesis, we assume that every microscopic state occurs with the same probability under constraint conditions. This is a working hypothesis, okay? This is working hypothesis. But if we assume such working hypothesis, in principle, we can calculate derivation functions for given systems. Then we have two different ways of answer to the question. What is the question? Question is to determine the most probable value of the energy distributions. One has the thermodynamic answer, in which energy distribution is obtained as the maximum value of the total entropy. This is the answer of thermodynamics. And if we assume this one, most probable value is given by minimization of Reich functions. And surprisingly, I is convex functions, and entropy can be concave functions. And actually, the concavity of the entropy function can be obtained by additivity and second law of thermodynamics. And so these two different ways should give the same answer, because energy distribution can be obtained as an experimental result. So the energy distribution is a, how to say, natural phenomenon which are independent of framework of descriptions. So this gives quite natural conjecture. Minus means that convexity and concavity relations, and some proportional constant S this is a conjecture. This is a conjecture. And because maximization of the entropy gives the most probable value, and the minimization of the I gives the entropy, and also I should be 0 at the minimum value, so maybe we have some constant values. Okay. This is a conjecture. Then we can analyze specific systems. So even idealized gas. So if we study the idealized gas, we can calculate Reich dimension functions, okay, by using a principle of recall rate. Actually, we can calculate the Reich dimension functions in the assumptions of the principle recall rate. And in the case of idealized gas, we already know the thermodynamics. Then we can compare these two quantities. Then we find that actually this proportional constant is equal to NKB. I'm sorry, I made a mistake. Okay, I just put N. S is the extensive quantities, and the I is independent of N, and we just put the N here. Then in the case of idealized gas, we can calculate K is under volume. So of course, this is reserved for the idealized gas cases, but in a viewpoint, optimistic viewpoint, we can assume that this type of relation might be valid for any material. Of course, this is assumptions. Then, more precisely speaking, Reich division function might be proportional to entropy function, and the proportional constant itself depends on the choice of the material. Of course, it is one possibility, but this framework is elegant and this framework is elegant, so we just expect that these proportional constants are independent of the choice of material. And in the case of idealized gas is given by the Boltzmann constant, inverse of the Boltzmann constant. So we can check these relations by different materials. Then, surprisingly, I want to say this is really surprising fact. Surprisingly, and for all materials, realization function is proportional to the entropy difference. And proportional constant is given by the inverse of Boltzmann constant, which can be justified by experiments. So that's why now we can say this is fundamental principle. Now we know that, and maybe you know, you already know the foundation of statistical mechanics, and every textbook starts with the stating that this principle. Of course, we already know that this principle might be correct for equilibrium systems, but history of establishment might be not so easy. And as I say, this is just more stimulating. And this, yes, because this type of understanding was proposed by Einstein. This is an Einstein formula from 1987. Do you know that this formula? No. But you know that five Einstein formula. Okay, now you learn the six Einstein formula. So, of course, at Gibbs formulated the equilibrium statistical mechanics in 1902, and Einstein developed statistical mechanics in 1904, just before Brownian motions. And Boltzmann, of course, already proposed a framework of statistical mechanics, and interpreting the papers of Einstein, we can now understand his work, claiming that, assuming that realization function is related to some of the functions, and this might be related to the microscopic assumptions and checking. His attitude always stands on the experimental verification. Important thing that, you know, we never check principle of equal weight, right? But because we don't check the we cannot count the frequency of microscopic state. So we never check the principle of equal weight. But we can check realization function in experiments, right? And we can check some of the functions. Oh yes. For example, this is related to fluctuations, and this is related to thermodynamics, and thermodynamics obtained by response measurement. For example, the heat capacity is given by how energy is transferred to the by the increment of the temperatures. So this formula is important because fluctuation property can be measured in experiment, and response property can be obtained in experiment. For example, if we know the data, experimental data of heat capacity and the equation of state, we can have the we can construct entropy functions. And also, if we can measure fluctuation property carefully, then we can find realization functions. Then we can compare these two, and we can actually check this constant is universal or not, and the result is universal. And for example, one remarkable formula, simple formula, is maybe CB. heat capacity is given by energy fluctuations. David, which is, I don't know, minus T square, oh yes, something like that. This is a formula. Maybe you know that you can derive this formula by using the canonical ensemble or something like that. But this formula coming from this universal relations. Cv is determined by the fluctuation thermodynamics response, and the fluctuation is given by large deviation functions. Okay, so okay, so today's highlight is to these relations. So you remember this home and rephrase at night throwing the coins. Okay, so tomorrow I give you the this idea. Large deviation. Today I discuss a basic concept of large deviations, and I discuss dynamical behavior tomorrow. And I consider the large deviation dynamical behaviors. And by using the large deviation properties and large deviation functions, and the symmetry of large deviation, we can derive the motions of small particles. The result is obtained by Langevin equations. But the important thing is that Langevin equation can be obtained as the result of the symmetry of a large deviation function. This is tomorrow's topics. So, okay, so are there any questions about? Oh, yeah, okay.
Can you consider this large deviation function to be a sum of entropies in general?
Yes.
Can you?
Yes. Of course, this is very surprising fact, but result is follows. So large deviation function is proportional to the entropy, and the proportional constant is given by the inverse of Boltzmann constant. Really surprising fact, right? Yeah.
Can you please explain the principle of equal weight?
Sorry.
The principle of equal weight.
Principle of equal weight.
Can you please explain?
Can you explain the principle of equal weight?
Oh. Okay, so for a given systems, in that case, for a given systems, we have constraint, energy conservations. Then there are many microscopic realizations. Yeah. Then all microscopic configuration can be assumed to occur equal weight. Of course, okay, so you can imagine you can specify all the particles are located around here and around here. These are, of course, one microscopic state. But we assume this occurs at the same probability as this one. But, okay, you don't understand, you don't agree with this principle? Isolated system, yes. But okay, so for this system, we studied isolated systems, and in that case, we have just one constraint: total energy is conserved.